everyone, thanks for joining us today. Now that you've gotten a taste of the work that the MIT team has done over the past year, we'll dive into the details. NASA's 2020 Big Idea Challenge asked teams to develop payloads that will enable exploration and science of the moon's permanently shadowed regions, or PSRs, where there are critical deposits of ice that can be used to make drinking water and rocket fuel. Accessing this ice will enable sustainable exploration of the moon as part of NASA's Artemis program. But PSRs pose significant challenges to exploration, including limited or no line of sight to landers on the lunar surface. With this in mind, our team developed a lunar tower that will provide line of sight to a large swath of the lunar surface and the interior of a PSR, which will enable the delivery of services such as communications, power beaming, and remote sensing.
Going into this challenge a year ago, our team of graduate and undergraduate MIT students was interested in supporting the upcoming exploration of the lunar permanently shadowed regions. Over the last year, we designed, built, and tested a TRL-4 proof of concept for a deployable lunar tower. To shorten development times so that we could keep up with Artemis, our lunar tower concept elevates a CubeSat payload on top of a NASA flight-proven composite boom. The payload is positioned at a unique vantage point with valuable lines of sight to the PSR interior, to the lander, to nearby rovers, the Sun, the Earth, and even to other landers. The elevated payloads robustly support distributed exploration and science systems for robots and humans alike. Last March, the pandemic dispersed our team to 8 cities across 3 continents. Working together from Cambridge and Lee in Massachusetts, from Seattle and New York City, Columbia in South Carolina, Wollongong and Adelaide in Australia, and Nicosia, Cyprus, we divided and conquered the design and development of our lunar tower and completed our mission to demonstrate a TRL-4 proof of concept. My colleagues will now present our progress report with our findings and next steps.
In the remainder of this presentation, we want to focus on 4 key takeaways. First, we will discuss the technology development roadmap pursued by the MELT team, along with the steps we took to bring the project to a technology readiness level of 4, meaning that its components have been validated within a laboratory environment. We will also show how the work done so far in MELT satisfies all of the requirements and objectives set out by NASA as part of the 2020 Big Idea Challenge. Afterwards, our team will highlight a number of key ways in which MELT will enable sustainable lunar exploration by supporting both future robotic and human missions to the lunar surface. And finally, we will end the presentation by going over the next steps that are needed to progress MELT to a higher technology readiness level, so that the technology that our team has demonstrated can be deployed in support of the ongoing Artemis program. First, let's start out with a progress made by MELT on the project's technological development. So no new technology is produced in a vacuum. And with MELT, we're only able to achieve a rapid pace of technology development by leveraging existing, proven technology to meet a known capability gap previously identified by NASA. Concept work by NASA Ames as far back as 2017 highlighted the utility of lunar towers for providing moon missions with communication, power beaming, imaging, and scientific capabilities. However, traditional materials and designs for proposed lunar towers required significant mass budgets and were limited in height. Regardless, even 10-meter tall towers deployed on 1-ton landers were identified as providing a useful service for future missions. In MELT, we identified deployable composite booms as a way to overcome these limitations. This technology has already been looked at by NASA and others to help deploy solar arrays in orbit. In particular, the Rollout Solar Array, as shown here, is a technology demonstration mission to the ISS that showed how composite booms could enhance our capabilities in microgravity. With MELT, we seek to enhance this proven existing technology by developing and demonstrating how it can be used to vertically support a load on the lunar surface.
Okay, MELT is composed of 3 subsystems: the leveler, which sits near the base of this image that you see here, the deployer and the boom subsystem, which is most of the structure that you see, and finally the upper bus, which is the payload on top of the tower. Each of these is going to be described in more detail in the following sections, and we're going to start out with the leveler subsystem. So the primary job of the leveler subsystem is to autonomously correct for any slope that the lunar lander could land on. So for example, if the lander touches down on a hill, the leveler will automatically realign the system so that the tower can be deployed parallel to the gravity gradient field, avoiding a tip over. Even for a very tall boom, the leveler will be able to make sure that the system doesn't tip over by orienting it properly prior to deployment. It does this by first sensing the angle of the lander using the IMUs shown in the image on the right. These feed information to a control system that extends the 3 linear actuator legs that you see in the image on the left in such a way that the deployer mounting plate reorients to the proper position. The system is mounted to the lander using custom-built trunnion mounts, and the actuator legs are mounted to the deployer plate using universal joints. Many designs were considered when we were first building this system and coming up with the initial trade study, including hexapods and free-hanging platforms. But ultimately, we chose a modified Stewart platform that you see here based on mission constraints, the user guide from Astrobotic, and big idea judge feedback that we got from our initial submission. So this is a video here of one of our early prototypes that we built showing how the system works. And we've iterated on this design and prototyped it many different times in order to optimize the design for performance and also for mass, because mass is such an important metric in space missions. We also conducted thermal and stress analyses on the design before moving on to higher fidelity designs. You can see here that we built a couple of fully functional prototypes in the machine shop on campus, and we ended up running these through qualification tests. This included load tests with increasing mass, just to make sure that the linear actuator legs could actually support the full weight of the system. And then finally, we built a final version and ran it through its own testing series, which included a fully integrated system test, which is shown here. What you'll notice in the image is that the whole system is at an angle on a custom-built mock lander. It's at about 12 degrees slope, which is what we designed the system to accommodate. And you'll notice the IMU right in the center. It's the light right in the center of the screen here is going to sense that it's at an angle. The IMU then sends information to our control system, which calculates how much it needs to extend the linear actuator legs in order to get it to work. The system is designed to operate with 3 degrees of freedom in roll, pitch, and height in order to achieve the final position that we want. And it's also designed to support over 1.5 times the weight of the full system. It's using stepper motors to adjust these linear actuator legs. And what you see in the video is it's honing in on its final position. It takes a measurement, makes a calculation, adjusts the legs, and then repeats that step until it finalizes its position. One of the great things about this system is that once it finds its mark, the leveler passively locks itself. So it requires no power to hold its final position. It can be controlled autonomously or manually. Here in this video, we were controlling it autonomously. So it was doing all the movement and calculation itself. The operators were simply there to monitor data and safety systems.
Our approach to obtain a reliable self-leveling of the platform was to split up the process into 2 different steps. In step 1, we wish to determine what length each leg actuator should target based on our pre-existing knowledge of the system. In other words, from the desired height and orientation of the platform, as well as the measured lander orientation and our kinematics model of the system, we can derive a set of nonlinear equations that can be solved in real time to give us the desired leg actuator lengths. In theory, if our kinematic model of the system would be perfect, we wouldn't need any extra step after that. In practice, however, we compensate for inaccuracies of our model by correcting the desired platform level with its actual level being measured by an accelerometer. So in step 2, we feed this corrected desired platform level to our inverse kinematic solver of step 1 to finally obtain the corrected leg lengths.
The deployer works by combining 2 active collaborative mechanisms, a spool and a pulling roller system, helped by a 3D printed brace in between. The boom is wrapped around a 15-centimeter spool that pushes the boom through the 3D printed brace, guiding the boom from flat to deployed, while fixing the boundary condition at the base. The roller system pulls the boom out, overcoming any blooming or excess friction caused by the 3D printed brace structure. The speed of each motor is controlled to deploy the boom at a rate of approximately 0.8 millimeters per second. Reversing the direction of these mechanisms facilitates retraction of the boom. Here, we show a tour of the deployer computer model on the left and physical engineering model on the right. Note the significant adjustability of the bracing and roller geometries to allow both for the double omega boom geometry shown, as well as an interlocking C-shaped geometry soon to be enabled by current work.
These two types of booms are made from thin carbon fiber and are stable in their deployed or unrolled state. On the left is a lenticular or double omega cross-section boom. And on the right is an open circle cross-section with slit-locking technology to join the two edges. With thicknesses of less than 0.5 millimeter, they are extremely lightweight. At 0.1 kilograms, the boom consisted of just 0.4% of the total mass of the system. These booms are extremely strong, and these two designs in particular both mitigate torsional buckling. The deployer and boom subsystem was successfully tested to TRL4. The system deploys the boom to its full 2-meter length in about 30 minutes. In addition to its ability to work with different types of composite booms, the deployer can also support booms up to 16 meters in height. Though these booms are designed for microgravity, our deployer's bracing system fully supports the extended upper bus in Earth's gravity field. Through our testing, we determined the natural frequency of the fully extended boom, and we also measured the force and torque required by the motors to overcome friction and gravity.
The main function of the upper bus is to provide power, control, and data handling services to our client payloads. The upper bus platform is capable of azimuthal pointing to within 1 degree, allowing for both sun tracking to add redundancy to our power system, and to allow us to accommodate the observational needs of our client payloads. To facilitate an easy transition to flight-proven hardware, the entire system is designed around a standard 1U CubeSat form factor. Furthermore, to take advantage of the high availability solar power that we expect to find above the surface of the lunar poles, the upper bus is equipped with its own independent solar power system, allowing it to potentially survive the death of the lander and operate into the lunar night.
The solar power system supports the pointing and communication capabilities of the upper bus. Client payloads can communicate with the lander using Wi-Fi. Here, an HD camera serves as an example payload demonstrating the system's pointing and data transmission abilities. The subsystem has been validated to TRL4.
In order to enable the fast prototyping and testing of MELT, the team decided to use 2 readily available Raspberry Pi microcomputers to control our system. The main Raspberry Pi is mounted on the lander, and it manages the deployment and leveling operations, while the second one is mounted at the top of the tower, and it manages payload operations. Each microcomputer runs the open source ROS middleware, which facilitates communication between the 2 computers. It also allowed the team to reuse a lot of code that was written by other people in the robotics community. Finally, in order to interface the different devices needed to operate our system with the microcomputers, the team opted to use the TinkerForge standard components, which offer an easily expandable ecosystem of different commercial off-the-shelf sensors and communication systems.
The MELT system is designed to deploy and operate fully autonomously on the lunar surface. We've constrained our own designs using the mass and volume requirements given for lunar payloads by current commercial lunar payload services vehicles, such as the Astrobotic lander. MELT is packaged into a CLIPS lander and locked to the frame during launch with the systems powered off. During transit to the Moon, MELT is powered on and a full systems check is run. The CLIPS lander then delivers MELT to a landing site near a PSR, ready for deployment. Based on available CLIPS data, an incline of up to 12 degrees can be expected at the landing site. Our levelling system is designed to accommodate a 15-degree incline and performs an initial levelling operation at the base of the MELT system prior to deployment to correct for this lander slope. The boom is then deployed incrementally, with the deployment sequence halted to allow for subsequent levelling if needed. Additionally, if the levelling sensors detect a significant slope during deployment, such as a shift in the lander caused by a moonquake or other payload deployment, the deployment sequence can be halted to allow for this levelling. A lunar demonstration tower will be deployed to a full height of 16.5 metres. Once fully deployed, a full systems checkout is performed on any payloads on the upper bus. This includes a test of the camera and pointing systems, performing a 360-degree rotation and transmission of images of the PSR, and a test of the solar panels by sun tracking and rotating the bus to align solar panels with the sun. The levelling system is kept active in case a slope is detected. At the end of the mission, lasting one lunar polar day, all systems are powered off for end of life. We have conducted a full autonomous systems test of the levelling, deployment, and operations phases of the MELT prototype to a demonstration height of 2 metres. MELT meets the requirements and objectives set out by the 2020 Big Idea Challenge. Through development and rigorous testing, our team has developed a low-cost solution to support operations in and around permanently shadowed regions. Per the requirements outlined by Big Idea, the system draws 8 watts of continuous power and 40 watts peak power for 5 minutes during its operation. We transmit data to our control center at a bandwidth of 70 kilobits per second per kilogram of payload, and the components selected for the lunar system are rated to 1 kilorad of radiation. Our current test plan and path to flight set the goal of having all system components rated to TRL 6 or above, ready for launch in 2023. A key advantage of the MELT system is its ability to both accommodate a range of payloads on the upper bus and also support multiple payloads in and around PSRs. Through use of COTS systems and efficient design, MELT enables low-cost operation and builds on existing technologies, and is designed for packaging on current CLIPS providers.
This first prototype weighs in at 23 kilos, but there is a justification for exceeding the 15 kilo guideline. Let's consider a use case of MELT tower sharing a ride on an astrobotic lander with 5 cube rovers versus a similar lander with a second science payload in the place of the tower. The line-of-sight services provided by the tower ultimately result in reduced size, weight, and power demands for the 5 cube rovers and their payloads. If, for example, the mobile payloads could be hosted on 4 U cube rovers instead of 6 U cube rovers, then the 8 kilo excess mass of the tower would be exactly offset by savings in cube rover bus mass, without any reduction in the useful mass of the mobile payloads.
MELT supports lunar exploration by enabling key use cases for robotic and human exploration. MELT's ability to both deploy and retract enables it to be mounted on a lunar rover. This additional mobility would increase the flexibility of lunar exploration missions. By attaching a laser to MELT's upper bus, MELT can facilitate power beaming. Power beaming provides rovers with wireless charging to extend the travel capabilities of a rover exploring PSRs. Deploying multiple MELT towers would create a multi-tower ecosystem. By communicating with each other, these towers would facilitate a communications network across a lunar area of interest. Equipping MELT with a radio repeater would create a radio relay between the tower, a rover, a lander, and Earth. This would enable a communications network between all key nodes of a lunar exploration mission.
We developed a test plan to map out how to progress from component tests through ready for launch. Of the 4 phases in the plan, we originally planned to conduct the first 2 phases, shown in blue. We did successfully conduct all phase 1 testing, bringing MELT to TRL 4, which is validation in a laboratory environment. This involved component testing, interface fit checks, subsystem functional testing, integration, and system testing. However, COVID-related lab closures at MIT and NASA prevented us from conducting the phase 2 environmental testing that would have taken us to TRL 5. Our next steps focus on completing the rest of this test plan. This would include phase 2 testing, which will be performed at MIT and NASA centers, and we've already been in contact with both Kennedy Space Center and the Jet Propulsion Lab. From there, we'd continue along the test plan to test readiness for surface operations, launch, and flight. We would also need to incorporate specific steps along the way to ensure we fulfill requirements for TRL 6 through TRL 9, including potential in-space demonstrations. Our team is already looking into other funding opportunities, such as NASA's PRISM and Luster solicitations. For those solicitations, we've collaborated with other organizations, including the German Space Agency, NASA Langley, another MIT research group, and 2 commercial space companies.
MELT towers can facilitate other big idea projects through our elevated payload. By providing a larger field of view, we can maximize the area for power beaming. This would extend the capability of the laser and Bell laser power delivery systems in the Big Idea Challenge. With the extended power delivery and communication, the towers can act as a base station for mobile rovers. The mobile systems can have onboard instrumentation for soil characterization, drilling, and mining. In addition, ballistically deployed sensors like VELOS would strongly benefit from the long-range communication enabled by high-altitude towers. NASA's lunar ISRU strategy incorporates plans for lunar prospecting, exploration rovers, and manned missions within PSRs. These objectives focus on mobile systems to evaluate and mine minerals, as well as collect water, oxygen, and construction materials. MELT solves an important challenge to enable exploration and development of these ISRUs in the PSR. With a tall structure at the edge of a shadowed region, an elevated payload can distribute energy to these mobile systems. An elevated payload on the tower can also establish long-range communication and positioning systems within the PSR. When multiple MELT towers are deployed on the lunar surface, we can create an interconnected power and communication grid. These towers act as nodes in a mesh network to create a versatile ecosystem to cover a wide area on the surface of the moon. With the flexibility and modularity of MELT towers, NASA will be able to have a high-fidelity data transfer, greater mass savings, a larger power budget for scientific instrumentation, and the ability to explore a larger area within the PSR.
Our team is seeking additional funding to continue development of MELT. Additional funding will allow us to do several things. We would test different boom geometries and heights in order to find the optimal geometry and to achieve our goal of building a 16-meter tower. We would pursue the environmental tests that we were prevented from running because of COVID-related lab closures at MIT and NASA. We would finish development of a photogrammetry functionality, which would sense the position of the upper bus and thus identify any static deflections in the tower that need to be resolved. We would decrease system mass in order to take up less space on Eclipse lander. Finally, continued development would allow us to retire more risk and increase TRL until MELT is ready for flight. Thanks for your time today, and we hope you join us on our journey to the moon.